In episode 44, Conduct Penetration and Fuzz Testing with Purpose, we shift attention to two of the most intensive classes of security testing and ask a simple question: what are they actually for? Penetration testing and fuzzing often attract interest because they look dramatic, generate screenshots, and sometimes even make headlines. However, for serious assurance, the real value comes from how these activities are framed, executed, and translated into durable improvements. The focus is on realistic objectives, not theatrical stunts that impress in a slide deck but do little to change risk. When handled with purpose, these tests become surgical tools in the security program rather than irregular performances. Purposeful work starts with defining target goals, rules of engagement, and safety constraints before anyone launches a tool. Goals might include validating that a new payment flow resists common web exploitation techniques, assessing whether segmentation truly limits lateral movement, or testing that an application programming interface cannot be driven into unsafe states. Rules of engagement define boundaries, such as which systems are in scope, which techniques are prohibited, and what hours testing may occur. Safety constraints cover limits on data modification, transaction values, and performance impact, particularly in production or production-like environments. By fixing these elements in writing, organizations reduce ambiguity and protect both operations and testers. Providing good architecture context and known risk information to testers can dramatically accelerate discovery. Many organizations still treat penetration testing as a contest where the tester is kept in the dark to prove their skill, but this usually wastes time on rediscovering basic facts. A more mature approach shares high-level diagrams, data flow descriptions, trust boundaries, and key technology choices up front. It may also include a summary of known issues, prior incident themes, and high-risk assumptions the organization already worries about, such as reliance on a particular legacy component. With this material, testers can spend more energy on exploring difficult, high-impact paths instead of guessing how the system is wired together. Blending black box, gray box, and white box approaches produces richer and more actionable findings than relying on a single style. Black box perspectives, where testers have only external access, simulate what an outsider can do with minimal information and help reveal obvious misconfigurations or poor exposure decisions. Gray box work adds limited internal knowledge or credentials, representing an attacker with some foothold or an insider with constrained access. White box techniques extend visibility further, bringing in source code snippets, configuration files, and detailed design notes. When the engagement weaves these modes together, the resulting report shows both how an attack unfolds from the outside and where specific internal weaknesses made it possible. Chaining vulnerabilities is one of the most important skills in penetration testing because real attackers rarely rely on a single flaw. A configuration weakness might enable information leakage, which then makes it easier to exploit a subtle input validation error, which in turn exposes credentials that unlock a powerful administrative feature. Purposeful testing documents these chains clearly, showing step-by-step how minor issues combine into serious outcomes, such as unauthorized fund movement or complete control of a cardholder data environment. At the same time, exploitation scenarios should remain credible and bounded, avoiding unnecessary damage or unrealistic assumptions. This balance helps stakeholders understand both the severity and the practicality of the risk. Fuzz testing introduces a different but complementary way of exploring weaknesses, and it also benefits from deliberate strategy. Fuzzers can operate on mutation strategies, where they take valid inputs and introduce random or guided changes, or generation strategies, where they build inputs from scratch based on a model. Protocol-aware, grammar-based fuzzing adds another layer by respecting the structure of complex formats or communication protocols, which tends to uncover deeper and more subtle errors. Choosing among these approaches depends on the nature of the target, the availability of specifications, and the maturity of existing tests. When strategies are chosen thoughtfully, fuzzing becomes a powerful way to probe resilience beyond normal usage patterns. Effective fuzzing also depends heavily on instrumenting targets so that meaningful signals are captured. Many bugs uncovered by fuzzers do not show up as obvious crashes. Instead, they appear as hangs, resource exhaustion, or silent data corruption. Instrumentation that tracks code coverage, memory safety violations, and entry into unusual error paths helps guide the fuzzer toward unexplored regions of the code. It also helps distinguish between harmless anomalies and true security-relevant issues. By monitoring these signals, teams can tune fuzzing campaigns over time, focusing effort where the returns are highest. Without this instrumentation, fuzzing risks becoming a noisy but opaque process. Once penetration and fuzz testing start producing results, prioritizing findings becomes essential. Not every discovered fault has the same practical significance, even if it looks dramatic in isolation. A mature program evaluates issues based on exploitability, blast radius, and the level of effort a plausible attacker would need to invest. For example, a flaw that requires highly specialized access and complex setup may be important but less urgent than a simple misconfiguration that any authenticated user could abuse. Prioritization criteria, grounded in risk rather than mere technical novelty, help leadership and product teams allocate remediation capacity wisely. Delivering proof-of-concept material responsibly is another hallmark of professional work. Proof-of-concept exploits should demonstrate that a vulnerability is real and exploitable, but they should avoid exposing sensitive data unnecessarily or handing over dangerous tools without controls. Reports should include clearly written reproduction steps, sanitized screenshots or logs, and explicit cleanup guidance so others can safely confirm behavior. Where possible, proofs should avoid reusable payloads that could be misused outside the testing context. This careful handling shows respect for the organization's risk and helps maintain trust between testers, defenders, and assessors. Coordinating fix sprints and retesting activities ensures that the value of intense testing is not lost after the report is delivered. When significant issues are identified, owners, timelines, and expected outcomes should be captured in the same planning systems that handle other engineering work. Retesting should verify not only that specific exploits no longer work, but also that underlying root causes, such as insecure patterns or library choices, have been addressed. This cycle of fix and revalidate turns one-time findings into lasting improvements. Evidence preservation is especially important for penetration and fuzz testing, given the complexity of the activities. Inputs, seeds, and configuration files used by fuzzers should be stored in a controlled repository so that future campaigns can be compared and extended. For penetration tests, key artifacts such as selected request and response pairs, relevant log extracts, and screenshots help reconstruct the path to each finding. Telemetry from instrumentation and supporting systems can also be invaluable when later investigating incidents or explaining behavior to assessors. Keeping this evidence organized and accessible turns each engagement into a resource that can be reused rather than a fleeting event. Sharing lessons broadly may be the most powerful way to amplify the impact of these deep tests. Findings from a single application or system often reveal patterns that apply across a wider portfolio, such as recurring issues in input validation, cryptographic usage, or access control design. Capturing these themes and converting them into recommended patterns, hardened libraries, or secure defaults allows other teams to avoid the same mistakes. Internal knowledge sessions, updated coding standards, and improved template configurations can all flow from one well-run engagement. In this way, penetration and fuzz testing become engines of organizational learning rather than isolated technical exercises. A brief mental review of purposeful penetration and fuzz testing brings together several recurring themes. Clear objectives and rules of engagement create guardrails that keep testing focused and safe. Blended methods and vulnerability chaining show how different perspectives and small issues combine into meaningful risk. Structured fuzzing strategies and strong instrumentation keep exploration guided rather than random, while thoughtful prioritization and retesting ensure that the most important issues are addressed promptly. Knowledge sharing then carries these insights into development practices, architecture decisions, and future testing campaigns. Seen together, these elements define what it means to test deeply with intent rather than spectacle. The practical conclusion for episode 44 is that these powerful techniques deserve structured treatment, not ad hoc scheduling. Many organizations benefit from periodically scheduling focused penetration and fuzz testing engagements against carefully selected targets, such as new payment services, major architectural shifts, or historically fragile components. Preparing a clear rules of engagement packet in advance, complete with objectives, constraints, architecture context, and contact points, sets the tone for disciplined work. As these engagements produce findings, linking them to requirements and control objectives creates traceability that serves both operational risk management and formal assessment needs. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.